Hi, my name is Matt Duff, and today we're going to talk about different filter responses. I've listed the 5 most popular filter responses up on the board here, and you can see that I've grouped them. The top 3 are all pole responses, and the bottom 2 are pole and zero responses. So these, since they require zeros in the frequency domain, they give you some more flexibility, and you can make a sharper cutoff. But the trade-off is that the circuitry, especially when you're doing an active filter design, is a lot more complicated. So typically you won't see these in active filter design. So we're going to concentrate on these top 3 up here. And as you move down this continuum, you have a trade-off between a sharper frequency cutoff as you go down, but your time domain performance gets worse. And I think the best way to see this is by using a computer program.
So we can use this slider in the Filter Wizard program to change the filter responses. I can move it over here to the right and make a Bessel response, or move it all the way to the left and make a Chebyshev response. So you can see that on the Chebyshev we only need a 3rd order filter, but if we move to the Butterworth we need a 6th order filter to get the same cutoff frequencies of 10 kilohertz and below 40 kilohertz. But on the other hand, when we go and we look at the step response, we can see that the step response for the Bessel filter is really good. But as we move over to the Chebyshev filter, then it looks pretty bad, and the Butterworth will be kind of in the middle here.
So we've seen that these different filter responses have different trade-offs, but let's see if we can understand a little bit better why these trade-offs are actually occurring. So in order to do this, I'm going to use an example. I'm going to use an example of a 4th order filter, and a 4th order filter is created by combining 2 2nd order stages. So what we're going to do is we're going to plot the 2nd order stages on these 2 graphs for both a Chebyshev and a Bessel, and then we're going to combine them to get the final response. So the final response, what we're trying to do is get a cutoff frequency at this dotted line here. So let's do Chebyshev first. So one of the stages is going to look something like this. And you can see that this stage has a cutoff frequency way before the cutoff frequency that we want. And so in order to counteract this, what we do is we have another stage that looks something like this, say. And when we combine the 2 stages together, then we should get something like this. So you can see some attributes of the Chebyshev filter here. So one is you get these peaks that you typically see in a Chebyshev filter. Another thing that you can see is that we get a very sharp cutoff because we're using this extra peaking of this 2nd stage, which has this very sharp transition. And so the final result has a very sharp transition. On the other hand, we're using these stages that have a lot of peaking, and so, in other words, these stages that are nearly unstable, which means that they're going to have a lot of ringing in the time domain. And so the Chebyshev does not have very good time domain response. So now if we compare that to what we see with a Bessel, so if I draw one of the stages, maybe with a Bessel, something like this. And then if I draw another one of the stages, maybe it looks something like this. So you can see we have these very lazy roll-offs. And so then the final filter response maybe looks something like that, right? So you can see that we have this very slow transition from the pass band to the stop band compared to the Chebyshev. But on the other hand, we're using very stable stages. And because these stages are very stable, are almost underdamped, they're not going to have ringing, and so the final result has very good time domain response. So we looked at the extremes, the Chebyshev and the Bessel. The Butterworth would be kind of in the middle. So that's why you see this different performance from the different filter types.